Hello, everyone. So today I want to talk about the paper on that called the Latent Space Oddity. But in general, this paper was kind of an invitation to investigate latent space in generative models. So that paper was uh, accepted at ICLR in 2018, and back then actually it got somehow mixed reviews because some claimed that this paper is just bringing all known knowledge from differential geometry, for example, into the machine learning, so to say. But
But
it's
that's
actually,
great. Yes.
yeah, that's great. And yeah,
If
so
that's the
that
case,
was
that's
that
great.
was a real invitation, and it started a small topic on itself. Um, and now different methods uh, use some ideas from that. So yeah, let's talk about that. So that's okay. Some other papers that represent a similar idea or were based on this paper. Um, so let's start from the reminder what generative models do. So you can think about that as you have two spaces. You have space of data, like where's your data set embedded. So that's something which has incredibly high dimensionality. And on the other hand, you have something that you can control. That's latent space on somewhat smaller dimensionality. And basically, what is neural network is just some mapping from one domain to another. And here we can represent that with some function g, for example, which translates from the Latin space, where we usually have um, Euclidean metric, and it is basically constructed by us. And this neural network trains to produce some mapping from Latin
Sorry,
space.
sorry,
That's,
Dmitry.
yeah.
There is no metric there. It's just a space without metric. There is no metric in the boundary in the dataset space. Why are you saying it's Euclidean,
In a
Dmitry?
in the data set space, well, there is
There's
uh,
no notion of distances. You just decide to, distance is something else you have to put on top of the data set if you want to have
yes,
metric.
okay, so there is actually a very okay, there is a hypothesis, let's put it this way, that uh among all your data that you have, well, okay, your actual data set lies on some manifold, right, of lower dimensionality of whatever the space of the whole possible data. And with that hypothesis, you you have your manifold, and you assume that your data set is actually samples from some manifold. And well, you want to study how this works. Uh, of course, there should be well, notion of distance. You somehow apply that to this manifold. You have to um,
I mean, data
introduce
set
that
doesn't
somehow.
come with a metric. Data set is
Data
just
set,
collection.
yes, data
So
set
if there
doesn't
is
come
some
with
kind of
metric.
notion of closeness of some samples from
Uh,
data, that's up to the loss function to maybe loss functions
yes, of
addresses
course,
it,
yes,
but the data
yes.
set doesn't come with it. Yeah.
Well, that's kind of philosophical for me because it depends on you. Okay, it doesn't come with data set as some function that you have on paper, for example, but with that notion, with that assumption that your data set is just samples from some manifold, then somehow induces uh, well, manifold, well, meaning that there is some space with metric.
Well, if
Well,
you assume that there is metric, of course there is metric, but I'm saying that if you just take a data set, it's just data set. It's a collection of numbers. Of course, you can assume there is
well,
some
I
preferred
mean,
metric
from
that
this
haven't
point of
been.
view,
Yeah.
you can treat everything as just collection of numbers, but
No, sometimes you have metric. Like I'm sure what you're going to argue is that this manifold of the latent space, there is a metric there, right? So
yes,
there, but it's a kind of
because
emergent metric that emerged from learning dynamics or something like that. Okay, sorry. I mean, I didn't
well,
mean
with
to.
latent space, okay, well, that's actually a very interesting
Yeah.
question. So in the latent space, that's a different story because we construct it by ourselves, okay? So that's something that we have in hands. If you want specific metrics there, we can do that.
Yeah.
Usually we do just Euclidean, right? We have just Kroneckers, um, delta. Okay, but with data set, we assume that's a hypothesis that this data set lies on some Hamming higher dimensionality manifold, and we want to study whether there is a good metric on that or not, etc. That's actually a very good question.
And maybe the other point, since we're on the very first slide, this latent space also doesn't have to be a lower dimensionality. I can easily imagine that your input space has some clever coding of high dimensionality state in there, high precision digits, and then really what really is this latent space should naturally be of a higher dimensionality than Z. And so it works both ways. Yes, normally you would want to compress your data, but sometimes there's some features hiding in the precise specifications of the boundary data of the data set data. But go ahead. Sorry.
Yeah, yeah. Um, So yes, so for this talk, for this paper, we're gonna keep in head that we have that mapping from our latent space. Okay, and we assume that we can work in that space. We know that how it's constructed, so it can be easily manipulated, so to say. And data manifold, uh, we will assume that there is a manifold, but we cannot access it. Uh, what we have is that we have some data samples from that manifold. Okay, and with that, um, let's talk just a bit on how generative models work. Um, so they usually learn the distribution. So how do you, for example, if you want to generate um, apple, okay, you take some point in your latent space, which if you take it at random, that's Gaussian, and your neural network learns the mapping. Okay, so you have from your latent space or generation space labeled here to your data space. And basically, if you have at first just data samples, you train your neural network to reproduce something similar to your data points. All right, so it learns some distribution around your data space available to you. And then when people have that, this process called generation, you input there some noise in the latent space, and that produces you your data point.
Which one is latent space? There are three spaces there. Which one do you call latent space?
Um, well, I would say generation space, you would call that latent space. Um, so here yeah, you could also try to shift that somehow and to resemble. Okay, so that's actually one of the topics that's going to be covered in the paper. So the idea is that usually you want usually have your latent space like in the simplest form, like you sample Gaussians from there, but you might want to change that to uh, help. Let's say this way. So um, yeah, so that's going to be covered for now. You can just focus on that. There's latent space, data space, and we have some mapping. Even though here we have two arrows, you can think about them as a composition of two mappings, and so you have one mapping. Okay. So one problem that comes from that is if you want to use you trained your generator, but you don't actually know, you don't sure that it represents the data from the real world, let's say, um, in a meaningful way, um, saying that, for example, as a human, you have some notion that some samples are closer to each other than others. Um, and this is how it should be. Well, neural networks, they train some mapping, uh, which doesn't have to be interpretable in any way. So here is an example from this paper where you have your MNIST data set, for example, and you have two classes, zeros and ones. So it might seem that in a latent space, is those a latent space that produce a data sample at the end of generation. So if you use Euclidean distance on that latent space, you may have like weird geometry. So your distance in latent space will not represent the distance, or what would you call a distance on data space. And so you want to change this. So
But what would you call, again, we're back to the question number one, right? What do you call a distance in
yes,
the data space? There is no such thing, right? So it just comes only once you put the loss function, only when you say, you say that these two classes are closer and these are different classes. Once you have that, yeah, then there is a notion of distance for
yes, of course, of
so you have to
course.
supply it. So you have to tell the data set that there is also a notion of distances. Otherwise, it's
Of course, yes. So in this example, we say that there is two classes, right? We have labels for them. And so it would be in our common sense that representatives of the same class should be closer to each other, right? And just a simple example, but it can be extended to high images, right? So actually, when this paper came out, was tested on variational autoencoders and GANs, but since then, diffusion models were announced, and so it can be tested there. And like a few recent papers, they try to investigate the latent space of diffusion models, and there it actually this question of what is the distance on the data set becomes very interesting. For example, yeah, I have it here. So might be too small, sorry. So for example, that's the latent representation of the, okay, yeah, that's, so that's output of diffusion. It is on the grid because that's some interpolation or grid in the latent space. So you take some slice of latent space, two-dimensional, and you make a grid on that slice, and you produce an image from each point on your latent space. Therefore, you have some grid of images. So the problem here is the same. Like, what would be a distance between images? Because, well, here actually you don't even have classes by themselves, meaning that, well, diffusion produces something, and then human looks at these pictures, and he decides, well, yeah, it seems like here's like some snow in the mountains. Okay, here's some cat, some cars. Uh, okay, but they were sampled equidistantly on the latent space. If there is any metrics that we want to embed, uh, let's say that we want to pull back on the latent space from the image data space, right? Because now if we say, okay, we want cars to be far, okay, so we want all cars to be closer to each other, but let's say it like cars don't resemble mountains, so let's put them away, and we can pull that notion back into latent space. So, okay, we bring some notion of metric on the data space, and we want to change our metric on the latent space in the way that changes accordingly. Okay, is there any questions?
Well, okay, let me. So you're talking about non-linear map, right? So of course you have a
Yes,
map,
yes, of course.
and then of course any non-linear map will produce you a distortion of the metric, right? So the metric that was flat in one space will be, but it's just a statement that neural networks use non-linear activation functions. Yes,
Um,
that's
yes. Though
that's kind of, and that's it. It applies to all neural networks. It doesn't only apply to this diffusion models.
though it's also actually important to know that even that you have nonlinear functions, it doesn't mean that the space that you have at the output is flat, right? So
It's not going to be flat because of the non-linearity. Even if you start with the even if you start with your metric defined by the loss function that we decide on the data
but
set.
actually it might be flat. It might be flat. So
Sure. But if it's flat, then it's a trivial problem, meaning you can solve it with the linear activation functions.
no. It might be flat with nonlinear activations. Okay, so it's basically again defined by your notion of the distance. Okay, so here you might see this picture as a composition of several phases
Yeah.
of the like of images, right?
Yeah.
And if you take one phase, it has uh closely to flat metric components, right? So if you just take like one square on in the corner, it's gonna be flat or
Well,
closely.
locally everything is flat. We're not interested about locally flat. I'm saying that globally, if the map is not linear, then you are like guaranteed to have a
Uh,
non-flat metric.
well, I see this again as somewhat philosophical because if you cannot,
It's mathematical.
if you can access only a limited number of images, and you have compact, okay, at the
Fine.
end,
Yeah.
and if that's local, like it's flat. I mean,
Then
uh,
to train a neural network, you don't need nonlinear activation function. If you're just working in this one corner where everything is flat data set and the latent space is flat, then to train this one corner, you don't need any nonlinear activation functions because the map
mm,
is just linear.
okay, yeah, but when you
So,
start, you
well, I'm
don't
saying
know
that
that.
this curvature space, which is of course the right way to look at it, but we know where it comes from. It's not like a mystery. It's because of the nonlinear activation. That's it.
Yes, but well, the question then, can you predict what's gonna be in one phase? Like
Yeah.
what parts are gonna be flat or what?
Yeah, you just well, after you train your neural network, well, not before you train, but once you train your neural network, you look at the map, okay, and you find, Jacobian and see how it changes, and you will see that it's produces a curvature in the space.
Yeah, yes, of course. I mean,
You can
yes,
calculate the curvature really locally and say, okay, look, this is not flat. You cannot choose new coordinates for which it will be flat everywhere. Locally,
yes.
you can do that, but globally, you won't be able. So I mean, it's just a more general statement, I think, than just generative models. It's like any neural network which uses nonlinear activation functions must have some metric associated with its internal degrees of freedom, which you call latent space. I call it bulk degree of freedom, but it doesn't matter.
Hmm.
No, I mean,
Well, yeah,
I
yeah.
think it's important point. Yeah. Also, it's not just only curvature. There's probably going to be places where curvature blows up and becomes singular, and there'll be. Do they talk about that? Because you can
Um,
really have curvature blowing up because of the type of the nonlinear transformations that we have.
yes. Well, again, as far as I know, it wasn't like
Okay.
it wasn't okay. It wasn't observed, I believe. So there's several papers that try that pullback method
Mhm.
where you have like pullback from the data space into latent space. Um, and I don't think any of them talk about singularity. Oh,
There'll be matrices that are not invertible, and so you
yeah,
still
yeah,
have
of
that.
course, of course.
And it's not
Uh,
just a projection; it's like more than that. Okay, fine. Go ahead. Sorry. Like,
yeah. No, that's actually a very interesting question because that's an essential part of the
right.
paper to understand what they're interesting. Okay, so okay, they have that definition. Okay, you have generator function. Okay, so they call that mapping from the latent space into data space as generator function. Um, okay, in general, if you want to investigate your distances, right, you can use that pullback
Hmm.
method. Okay, but okay, here they can you see that? Okay,
Yep.
because I have that Zoom window. Okay. Um, so yeah, as simple as that, if you have 2 points in the Latin space, then this distance described the following way with Jacobian J. Um, and we're gonna talk about this Jacobians a lot, actually. Um, okay. So is Jacobian again of nonlinear functions. That's neural network. We have some local basis, um, and that Jacobian um, okay measures the the surface, the volume. Um, that's well, they're not gonna use that though. Um, but we will see. We will see. Okay.
But hold on. The map from input to latent space is many to one. Yes?
Uh,
You you
No,
you you,
actually,
you did say that input space has
yeah,
high
yeah, yeah.
dimensionality.
Okay, actually, here they have in the paper, and we'll talk a bit about that later. 2 notions of generative function. So they have deterministic one, and they have the stochastic one. So the deterministic one is a mapping 1-to-1. Okay, so you fix your point in the latent space, you generate, for example, the exact image. Well, up to numerical error or whatever,
Yeah,
right?
but I don't understand that. The input space has high. I mean, Katya last time, of course, talked about how you can project out some of the dimensions in the input space, but but generally, your images of high dimensions than latent space. Like think about autoencoder, right? Latent space may be
Yeah.
sitting in some bottleneck. They're like you can have
Yes.
it's much smaller dimensionality, so So this is not
Well, consider this example. Okay, so here you have a slice of your data set, right?
okay, fine. So then you're not mapping it to all possible states of the input or of the
Yes, yes,
data
yes.
set, but only on a subspace. Okay, then it's exactly the same
Yeah, well,
which Katya was talking
yes,
about.
yes.
You just project out all the other directions and consider the mapping to
If you
that
have
subset.
deterministic generator, of course, that's going to be one-to-one mapping. So,
Well, it's not about, I mean, you can still have stochasticity in that map. They still have add noise to it. But the point is that there's this uh, there'll be the relevant directions to which you're gonna move once you move in the latent space, and there'll be orthogonal directions to which you don't move in the data set when you move in the latent space. And again, there'll be this problem of not or being able to globally define this map. You know, we always have this in differential geometry. Just think about your latent space being a sphere and
mhm,
the data set being a plane. Okay, so you'll have a problem of not being able to come up with one function that maps all points in one space to all points in one space. You'll need like to have two maps, and so
yeah.
locally this whole thing works. I am sure, but the globally, I mean, this wouldn't be possible in general.
Well, okay, yeah, but yeah, so as I see that, is that I imagine myself that Latin space will always have uh some as simple as grid, right, of parameters, well, or some uniform cube of parameters. And that is kind of one map.
Oh, yeah,
And
but we
what
don't
we can
know.
access and what we can access from the data
Right,
set is some mapping of this to the data set. So
right.
the whole data set, like imaginable data set, let's call it this way, can be more, but what we can access limited to this part.
Mm.
Okay, yeah, so we have this mapping. Um, okay, and here in this paper, they consider this function the autoencoder. So in this um, in this task, you have your encoder, which produces you actually some mean value and variance in the Latin space. And you have your decoder, which transfers back from the Latin space to the data point, right? So uh, the main point here for this paper is that we have two sub-blocks of the mean value and of the variance. Okay, so your neural network of
Mhm,
encoder gives you two values,
mhm,
mu and sigma, and then you produce point in the Latin space sampling from that distribution. So that equals mu plus some
mhm,
noise on that sigma. And then you take your decoder, which maps back from the Latin space to the data. Okay, so we have two sub-blocks here. The main, okay, so just a reminder. So now let's talk a bit about the curvature of that. Um, if we have some curve on our Latin space, right, which is mapping. So we have our function generator from Latin space to data space. We have our curve, which is defined as a Latin space. Um, we can compute the length of that, uh, and we can define the length on our data set by that curve from the latent space, for example, or actually we can do vice versa. So that's also a very important notion here that with your Jacobian, if it is known actually, that's a different point of the paper because they kind of have an assumption that, well, you have that, then you can go back and forth, right? Okay, yeah. So
Oh, the question for function f, if it's invertible everywhere, yes, and that's the Jacobian is non-singular everywhere.
yes, yes. Well,
Then you can always do that, of course.
yes, yes. So they have restrictions on the F, basically.
There is
They
another issue that you can have like non-trivial f's, but then your latent space would still be flat. So you'll have a Jacobian, you'll have metric, which is not Euclidean. It doesn't look like Euclidean metric, but it's actually
Mhm.
a flat metric in the appropriately defined coordinates. So like having J doesn't mean that you have a curved space. You have like curvature, like Ricci scalar.
Yes, yes, I think so.
Okay.
Um, yeah. Okay, let's move forward. Um, okay, yeah. So you can derive, uh, well, you can minimize that length to to compute your uh geodesics lines or like some others. And that's actually is not done in this paper, but it's done in the following ones. Also have that in the appendix of my presentation if we'll have time. Um, Basically, that's just a notion from differential geometry. Okay, but they don't actually use the notion of, okay, they use notion, like the definition of geodesics, but they don't give a recipe how to compute them on in a real case scenario. Like suppose that you have neural network and you want to compute that. It is not done in this paper, though there is a recipe in another one. I will talk about that briefly.
But hold on, if you already know that it's a flat metric,
Mm.
that in the dataset space, you're saying that still you don't know what the shortest distance in the latent space. Uh, so isn't it just going to be
Well.
following the shortened distance in dataset
it,
space and
it,
then
wait. Why does it? uh, It, it doesn't have to be flat in data space.
from what I saw, that's how they defined it. That the J was the only thing that was defined in metric.
Um,
So from what I saw, it is flat in the dataset space. Yeah, see? So this is a square. See there
yeah.
on the left-hand side of the equation too.
Yeah. Um,
That's how they define it, at least. And then it
yeah.
just looks like just a transformation to new variables. I don't even think that with this way, okay, it looks flat, curved. It's just
Yeah.
you just have different coordinates, but the thing is just still you can like start with Euclidean metric and define
Yes.
polar coordinates. Okay, and there will be some J for that, and it's a nonlinear transformation, but the space is still flat. The curvature, if you calculate the curvature, reach a curvature,
Mm-hmm.
scalar curvature, you will still get 0.
Yes. Well, as I see that, the main idea is that actually we want to uh not come from the Latin space and define the metric on the data space somehow, because of course that's a trivial mapping. Okay, even that we have deterministic generator. Okay, that's just some mapping. I mean, can make interpolations there, but on a data space, you define notion of distance based
No,
on
but
some.
again, now I'm completely confused, right? So let's say you do have a flat space for the data set.
For the data. Okay.
which is equation 2. Okay, now you go have some invertible function f that takes you to the latent space f. Then this new space, of course, will you can like push the metric there, and so it will have, it's just like rewriting the space in a new coordinates, and yeah, it will have.
Oh yeah, yeah. If you have flat data space, then yeah, that's
So there's nothing, no new curvature coming from the latent space in this, at least in this approach,
then
at what I
yes,
see.
then yes.
Okay, then it's okay. That's not what I thought. I thought there would be some emergent curvature that comes from the from this mapping, but here we don't seem to have that.
But yeah, if you have flat data space, then why would it be? Why would there be a emergent curvature in the
Well,
lattice?
if it's invertible f, of course, then there's at least in those places where f is invertible, uh, there's nothing there. But I don't know. Maybe this isn't the case. Maybe they're saying something else, and I'm confused.
Mhm. Okay, let's see. Let's see. So um, okay, so maybe we can get down to that when they introduce the stochastic generator. So they briefly discussed the deterministic generator F. Now you have these two parts. So your mapping consists of two functions and some noise sampled from the Gauss. Um, at basically the description. So here, the main idea that they have that in this scenario, your metric is now of two terms. One arises from a mean, one arises from the variance, right? So their main theorem one uh, explained that, right? So you have it's kind of average, right? That's expectation of your metric, but well, while you work with stochasticity, you will work with something of like expectations of some variables. And they prove that, which is pretty straightforward. So you basically have your definition of your function, your mapping, just write the derivative. Then you see that, well, basically what you have is derivative with respect to the first one, with respect to the second one, right? With the second one, that was Gaussian, that's variance. They write it like this. So there's matrices S, right? Yeah, random metric, they call it MZ. Okay, and now we want to take the expectation as term by term. If you look at A transpose, let's see, A transpose B. Okay, let me show you what is B once again. So we want to, okay, we have our J, which is matrix A of mean derivatives and B of variance derivatives, right? Then M, which is J squared, J transpose J is this term, right? So that's A transpose A, A transpose B, B transpose A, B transpose B. We can see that when you take A transpose B, because you have expectations of random noise, you will get 0. because we had mean for our Gaussian is to be 0. Then we take expectation of B transpose B, which is kind of cool property of that this expectation of noise, like matrix noise, gives you this product of diagonal transpose diagonal. That because, well, of the properties of our variances of our noise. So that's what we have here. So yeah, and the last term, I believe, yeah. So we calculated A transpose B. That's gonna be the same as B transpose A. We calculate B transpose B. What is left is A transpose A. I don't see that for some reason. Sorry. Wait. E transpose A should be somewhere. Okay.
Well, gross terms vanish and you only have like
Oh yeah,
right?
yeah.
Okay. So and you're saying now it becomes curved, really curved, so you cannot really diagonalize this metric everywhere globally. So with this additional term that comes from noise, is that the claim?
Well, they say that they say actually that with so you have here two terms, right? You have your mean and variance, and they say that with infinite number of data samples, let's say, your variance is gonna vanish, and then you have again the previous case, and so it's gonna be flat, I guess, right?
Hold on,
If you
hold
just
on,
have
hold on,
one
hold on.
term.
What is noisy here? Noisy here is the map F. Noisy
Map
here is
is
the neural network. Noisy here are the weights of the neural network that map you from the data set to the latent space. So that is what noisy. So you're making the map noisy, and then
yes.
with this map you define a metric differently, this way. And so, but now it is still a metric defined everywhere globally. Now this metric just cannot be represented uh, through, you cannot change the coordinates so
Yes.
that it becomes flat everywhere because of the way you define this metric. Yeah, and that I believe so. Probably before you would still have flat space, but now you have curvature because of this noise. But the noise is not coming from data; it comes from the neural network, from the weights, from the map.
Yeah, though, well, let's see. Okay, so they have the following statement.
Mhm.
So they have theorem 2, and they say, okay, yeah, sorry, that's a bit different statement. Okay, so they talk about the variance of the metric. So that's a component, that stochasticity that you have in your metric tensor. They say that this vanishes with your data dimensionality going to infinity, right? So that
Well,
means
it
that
depends on your network, right? I can certainly make my neural network noisy so that it has that.
well, I mean, here they have the pretty exact definition, right, of mapping. They
Yeah,
follow
but
this
sigma can be
Fourier
anything.
definition.
Yeah, the variance can
S-
be arbitrary.
Can be? I mean, if they if they follow the setup of Fourier, they have like predefined objective for mu and sigma.
No, it's not about objective, about the map. A map from the data set to the latent space, from the boundary to
Yes,
bulk.
yes.
from the the data set neurons to the internal hidden bulk neurons, latent space, whatever you want to call it. If this map is deterministic, then the function is invertible, and then you can always unwind your metric to be flat. But if it's not, and that's how they want to define the metric, then yeah, it will not be possible to
Well,
make diagonal to find the coordinates such that it's flat everywhere. You can still do it
well,
locally.
no. Okay, so there must be a confusion. So that variance, uh,
I was talking about
that's because yes, that's because no. That's actually because we have like the metric defined as
yeah,
random variable, right? So we have some expectation of it. Expectation is exactly this one.
yeah. Which
Yeah.
has some deterministic part, which is always there, plus the square of the sigma.
Yeah, but yeah, so that's already the expectation. So
It
variance
is.
going to zero doesn't change this formula.
Yeah, so variance is not, if variance goes to zero, of course, it becomes flat. But if the variance doesn't go to zero, it's not in general. I think that's the statement. And so the space is effectively curved.
Yeah. Um, okay,
Okay,
yeah.
good.
So that's actually their justification why that metric will work. So that's kind of will be good enough when you have high dimensional data.
Well, we don't know if this is a good definition of metric, but it's a definition of metric.
Yeah, that's a definition of metric. Then they say that this is a good approximation. So that's their claim.
To
Okay.
what?
I mean that the expected metric, expectation of m as good is a good approximation.
Who said it was good? Just they said this was good, or it
Yeah,
a
well,
good approximation of
that's their
what?
claim. That's their claim. I mean, yeah. So they say that
It's just a
this follows
definition of
from.
metric, which is, in order to decide if it's good or not, we have to define a loss function for which it's good. Mm, Yeah, but okay, no, I think I understand the way it comes
No,
from.
that's a good approximation. Not in like a good metric approximation, but a good
Approximation of
approximation
what?
of a metric, a metric.
Okay, so it's an approximation of a metric, which we
Yeah.
don't know if it's good or not, but it's has some. Yeah, but it makes sense. Sure, of course.
Mhm.
Thanks.
I think what they're saying is that it's they make some measurements at the end that says that you have better clustering results or something like that. So they have
Well,
some metrics that classify this as they put some numbers into why this is better.
yeah, but I think like good clustering results is your the boundary, the data set metric, and so that's one that you used from the very beginning. That's the one that you said was flat.
Yeah.
Uh, and then you use that metric to define a metric in the latent space, which is MZ. And now the question why MZ is the right metric. So yeah, maybe they just tried different
Yeah, well,
definitions of metric, and then this gave you the smallest. I don't know
also they
what
probably
actually.
have yeah, that notion that better metric is the one that produces better results. Yeah, as was said.
But
So
this metric is not used to produce results.
I mean, which one?
This MZ. MZ is just a definition. The way you produce results, you just generate a random point in the latent space and use this latent space to generate the image.
Yeah, we will talk about that later. I mean, they have.
Well, we're running out of time, so I don't know how much later, but
Okay, let's
uh,
actually
yeah.
skip maybe some. Okay, yeah. So they also define that with that um well Riemannian geodesics and Euclidean in Latin
Mhm.
space, right? So you have your notion there embedded now. Okay. Um, let's skip that and let's go to the experiments.
Mhm.
So actually, one important claim that they have is the following. Yeah, I don't want to skip that. Um, that whereas your variance is increased, that increases your metric, right? So that increases the distance in your latent space, right? So if you have, and where's that variance comes from, right? That's uncertainty of your model. So if your model, for example, haven't seen some data examples, and you now feed it to them, like you trained your model on zeros and ones, right? But now you give it like 6 or 7, whatever. Um, it it's at certain because it haven't seen it in the training set, and therefore it has a large variance in the so that has a large component of that variance metric, right? And it means that in latent space we have now where like distance go like far away, like from that region, which is unknown. So they claim is that that uncertainty produces boundaries for your known data set. So if you use that metric uh, that they claim to be good, you kind of keep yourself on the known part of that manifold. So that's one of the huge points in this paper, that there is kind of this emergent.
Okay, then the variance comes from the ensemble of neural networks. Basically,
No.
ensemble of neural networks with different weights. They haven't seen number 2, digit
No,
number 2.
that's I'm talking. The variance is that component. Okay.
Yeah,
That
I know,
component.
but it comes from the uncertainty in the map from the dataset space to the latent space. And in order for this to be more uncertain, you have to it has to do with the making the map random. So if a neural network was trained and it's frozen, the map from the dataset space to the latent space is not random. It's well defined. Okay, it's just a map. Now you want to make
No. But this definition of Vayer, again, you have your randomness there. Okay, because
yes,
you sample point in latent space randomly. You have your mean and
not
variance
no,
fixed.
it's not the randomness of Z. It's not the randomness of a Z. It's randomness of a map.
No, well, it depends
You're
on how
making
you
the
see
map
it.
random, not the Z random.
Wait. Uh, yes.
Okay,
It
so map is has to do with the randomness in the weights and biases.
no. I think we are not on the same page here. So, randomness here comes from the. Okay, yeah, you may say that comes from the weights, but no, we have frozen system now, right? And we have the stochasticity used to sample uh our like Z whatever. So we have the defined map as following, right? Where is it? Yeah, so we have some mean value, we have some sigma value, which are frozen, but we have noise all the way there, right? Epsilon is there.
Noise coming from where? So what f of z? F of z is a map from where to where?
From that to the data.
Okay, so is it mu means that there is I specify so z now it's in the latent space. So I specify z. Do I get a specific image or I get different images on the
If you just have mu, if you don't have
yeah.
yeah, you have
Yeah, okay.
one
So now a
specific.
question is you have this autoencoder architecture.
Yeah.
You specify some data in the bottleneck. Okay, and you keep doing it many times with the same Z. Will you get different pictures with exactly the same Z?
That's the case of deterministic generator. Okay, if
So
you don't
yeah.
have variance, that yes, you will have
Now, if
the
you want to add noise
exact
there, then
same.
you have to add
Yeah.
noise to this, activation dynamics from
To
bottleneck.
the map. Well, you make a map stochastic.
How do you make map stochastic? You make parameters in the map stochastic. Which parameters determine the map? The weights and biases. You can, of course, can have some noisy neuron that is connected there that makes biases or weights biases noisy. But that's how you make the map noisy, by making by considering distribution of networks, or by adding the noise by hand.
No, it's not. No, it's not. We have all weights frozen here. We have
Okay.
stochasticity in the map just from the sampler. You have your sampler from Gaussian. You add it to like in some way middle. Okay, so you have
Okay, but
your
that sampler just chooses different z's.
yeah. So
Okay, but then the map is not
that's a
stochastic.
Gaussian. That's a Gaussian.
Yeah, but that's the
from
map.
Z.
So z may be stochastic, but f of z is not stochastic. So you can have a stochastic z, a random z, and then your dynamics that takes you from z to the x hat is not stochastic.
I think it might be equivalent because they put like in section 2 they define the epsilon, and it's
Yeah,
I
you can
think the
make them
epsilon
equivalent.
can just come from the mapping, but it can also come from the
Yeah,
weights.
you can have like noisy neuron, and noisy neuron connects to your map, and then yes, and then that gives you randomness in the map. You can do that too. Yeah.
Okay, well,
Yeah.
it's kind of equivalent because, well, you can define a map as, well, a map of Z to the X is such as you take random variable around Z, first, and then maps it.
Yeah.
Map it. So
No,
that's
no, no.
also a
But no,
map.
no, no. If you take a random variable around z, you still map it with the same function. But if you
Okay,
have another random variable that you add to z, then you just have high dimensional space, and that high dimensional space, you just have one more variable to which you add, and that will participate in this map. Okay, well, I don't think we will resolve it now, but
yeah,
there
okay.
is some randomness in the map. Okay, and I would say that if this randomness comes from the random of map, then it's one thing. If it comes with a random z, then the map is not random. So where do you put randomness? That's the question.
Okay, okay, let's focus on results for
Mm-hmm.
last several minutes, I guess. Okay, yeah, so they provide an example of how you might use that boundaries of variance, of uncertainty,
Mm-hmm.
right? So they also talk about that, for example, if you have some input space, you want to reconstruct that from Bayer. So at first, your latent space might have some shape, but variance of that data might have like some arbitrary shape, which is in this picture. So they want to deform that in a way that you again have some boundaries around your known data. Okay, that's one of the applications there. Okay, so for that actually they provide neural network. Yes, so they use radial basis functions neural network, but let's not talk about it. Yeah, so that's one of the applications there. Then they tested that on the classification problem, that new definition of variance boundaries. They provide like high accuracy of classification there. Though I don't actually believe into these results because it doesn't provide enough. Though the paper provides the architecture for the both cases, that's kind of weird how they talk about that, like why they have so low quality on the linear one, etc. But well, that's like numerical justification of the method, and okay, they all they also talk about distant, which was actually defined in another paper by the same group, I guess. So with that distance, they kind of introduce sampling area. So they show that with their method, if you have data set of like zeros and ones, you can define good general Gaussians were like submanifolds of one data set, with one label and another label. And another interesting one, it's random walk. So with that notion of variance boundaries that they push away from their known regions, they run random walk in the Latent space. And well, of course, their method, it resembles Gaussian, so it kind of stays on the known data, but the Euclidean one goes away. So that feels kind of unfair, or like you could start random walk, not the Brownian, but with some lower Hurst coefficient or like some Levy flights, whatever. So that feels unfair. But yeah, well, they show that on the new common president. Well, that paper actually came out in the 2018, yeah, but
Still relevant today.
Yeah. Yeah, so they show that their method kind of stays on the manifold. Yeah, so I guess that was the main part of the paper. Yeah.
Thank you, Dmitry. For any questions, comments? Went way over time, but well, I've asked all my questions. Thank you, Dmitry. And next week we'll discuss DeepSeek, right? Thank you, guys. See you next week. Bye.
Bye-bye.
Well,